This is a lesson on interference of waves in the simple harmonic motion in waves unit. I had covered properties of waves prior, and what I'm going to point out relevant for this lesson is that the velocity of the wave is the wavelength times the frequency. When we look at interference of waves, we will be most interested in the wavelength, so that's how you can get to the wavelength. Wave interference is simply the adding of waves. In the most simple case, we will take two waves of the same frequency and same amplitude and add them together. When we do this, we must consider the principle of superposition. And superposition applies to adding more than just waves, but in the context of adding waves, it says when two or more waves arrive at the same point, the disturbances of each individual wave combine to create a resultant wave. And this may seem simple to you. What we're going to do is add waves in a very intuitive way, maybe. Notice I have two waves here, and they don't have the same wavelength and they don't have the same amplitude. At any point in space, though, they do have their own amplitude. And if I pick this one point in space, notice that they both have displacement above the undisturbed position. And when I add those two things, they will add up to the resultant wave. And this happens all across the wave. And we have two types of adding that happens. The first is constructive interference, or what is called reinforcements. And those two waves add together to create a larger disturbance than either one individually. And as you can imagine, there's destructive interference or cancellation when two waves create a smaller disturbance than each one individually. Okay, so we're going to look at three specific cases in here. One is perfectly constructive interference. The next one is perfectly destructive interference. And the third is anything that happens in between, right? If it's constructive, it may not be perfectly constructive. Another thing to note is that any difference in amplitude or frequency determines on how the two waves will add together. These two add into some sort of wobbly, wonky wave. You can see that here. It will repeat periodically because that's the nature of the wave. It will repeat periodically, and we will look at that, how it often that repeats. But for the simplest case, again, I'm going to look at same amplitude, same frequency. With perfectly constructive interference, you can see that there's two waves here, and they're getting added together at the points where they are at maximum displacement. We add those two together, and the resultant wave will be twice what one would be because they're both the same and they're adding together at the same spot constructively. And this is what we call perfectly constructive interference. The important thing to note is that the two crests are lining up with one another and the two troughs are lining up with one another, and so this constructive interference happens. What is important is that there's no shift, or if the two waves have been shifted one another, like if I take this second wave and I just pick it up and I slide it over and put it back down, I would need to slide it a whole wavelength over in order to get it to line up perfectly again and result in perfectly constructive interference. So when I have two sources, and this is where I'm going, let's call this source 1 and this source 2, and I have some receiver over here. A wave from the first source will travel a distance L1. A wave from the second source will travel a distance L2. And when I look at those differences, and you can take an absolute value, I always think of this number in terms of a positive value. When I subtract those two lengths, I have to get a whole wavelength shift difference, okay? And it could just be that they travel the same distance so that there's no path length difference. It's zero. They both travel the same distance so that when that wave gets to the receiver, the peak on one and the peak on the other are lining up on one another, or the trough on one or the trough on the other lining up with one another. There's no path length difference. All right, so that's what we call a path length difference. And you can see below here, it's denoted with a delta L. L1 minus L2. And again, always make this a positive value. Don't worry about negatives here. The path length difference, if we want perfectly constructive interference, has to be an integer multiplied by the wavelength. One whole wavelength, two whole wavelengths, three whole wavelengths, or zero wavelengths, right? That could result in perfectly constructive interference as well. So delta L is the path length difference. Again, notice that the wavelength, like I said on the previous slide, the wavelength is an important property here. So we have the wavelength in there, and m is some integer value. And I have plus or minus in here. Again, when I think of this stuff, I only consider positives. It makes it much easier. When considering destructive interference, when I have those two sources, I will still have a path length difference to the receiver. So there's an L1 and an L2. But what happens here is because we want zero, perfectly destructive interference, and you can see the resultant wave down here, has nothing. There's no wave left over, which means if one wave is cresting, the other wave must be troughing, so that we get a displacement upward and a displacement downward, adding to zero. And that happens all along the wave. So when we look at the path length difference, what happens is, and you may notice this wave 2 is shifted half a wavelength away from wave 1. If I took wave 2 and I shifted it just half a wavelength, they would line up with one another. But as it is, they're shifted by half a wavelength, and so we get the crests lining up with troughs all across here. So when I look at the path length difference, I want it to be what we call an half integer wavelength. So I'm going to take some integer and add on just a half, and we call that a half integer. Half integer. A half integer of the wavelength. And when that happens, we get this shift, and that results in perfectly destructive interference. What happens is that doesn't happen all the time. There's not perfectly interfering waves. There could be some place between perfectly constructive interference and perfectly destructive interference, which is what my first example was. This is not them amplifying each other, and this is not them canceling each other out. There's some sort of in-between happening. Any other phase difference will cause constructive or destructive interference depending on the phase difference, wavelength difference as well. So the path length difference between the two waves is neither an integer or half integer. That will not happen. So when you look at maybe a ratio of delta L over the wavelength, if it was constructive interference, we would expect it to be just an integer value. That's constructive. If it was destructive interference, we would expect it to be a half integer, and that's destructive interference. When we do this, it's n that's not equal to a whole integer and not equal to a half integer. It will be, for example, 0.6742. That's not a whole integer or a half integer. When I take the path length difference and I divide by the wavelength, I could end up with some arbitrary fraction. I don't know what it would be. It could be any number. So constructive and destructive interference, the perfectly constructive and perfectly destructive interference, are very special cases of interference. Otherwise, we get this not perfectly interfering. And I've shown you the example down here with water waves. This is from Hewitt, Conceptual Physics. And you can see that there's areas of destructive interference where the waves of the two sources have canceled out one another. That's perfectly destructive. And in between, we have some sort of perfectly constructive where the waves have amplified one another. At any other point, we don't have either of those. Not perfectly interfering, okay? So be aware of that. It's not just constructive or destructive. There's lots of ways that two waves can interfere with one another. And we're looking specifically at either perfectly constructive or perfectly destructive. I picked a couple of examples to exemplify these concepts. The first is two speakers, one, and I put the equations up here for us. Two speakers, one directly behind another, are each generating a 245 hertz sound wave. What is the smallest separation distance between the speakers that will produce destructive interference at a listener standing in front of them? The speed of sound is 343 meters. Okay, so I see a frequency and I see a speed, so that would let me find the wavelength. So I'm going to put a pin in that for a second and think about what's going on with the speakers. So let's call this speaker 1 and let's call this speaker 2. And there's a listener over here, some sort of receiver. What I know is that speaker 1 is going to have a distance L1 and speaker 2 is going to have a distance L2. And they want to know this distance in between. What is the smallest separation distance from here to here? And when I look at that, that's L1 minus L2, and that is the path length difference. Delta L is L1 minus L2, and they're asking for that. They don't give me any other distances in the problem. Notice they don't tell me what L1 is or what L2 is or how far that receiver is. That's just the setup that I'm given. So I want destructive interference, so that tells me I want this path length difference equal to a half integer of the wavelength. I'm just going to write that down. Delta L is, and they want what is the smallest separation distance. The smallest separation distance is going to happen when m equals 0. So I'm going to put that out here, smallest. So delta L has to equal a half of the wavelength. It doesn't matter how far those distances are. When I subtract them, all it has to equal is a half of the wavelength. So I can put that in there, half of the wavelength. Well, the wavelength is the wave speed divided by the frequency. And so I get a half times 343 divided by 245. Well, the wavelength of this wave, if you calculate it, is 1.4 meters. So that means these two speakers have to be 0.7 meters apart from each other. And a receiver standing any place along this line will not hear anything. These two waves will cancel out. The second problem I've chosen I called two speakers 2. Two speakers are wired to emit identical sounds in unison. The wavelength and error of the sounds is 6 meters. Okay, so they give me the wavelength, and that's good. I just need the wavelength. State whether the sounds interfere constructively or destructively when you're at a distance of 12 meters from both speakers, 9 meters from both speakers, and 9 from one and 12 from the other. So I'm going to draw two speakers. Here's speaker 1 and here's speaker 2. We don't know what their distance is. What we really care about is how far we are. So there's the receiver. And I'm going to note that there's an L1 and an L2. In the first situation for part A, L1 equals 12 and L2 equals 12. And when I look at the path length difference, when I calculate the path length difference, I'm going to take the absolute value of the difference of those. So I get 12 minus 12, which is 0. So when I look at this, I have an integer 0 value. There's no wavelength shift. And what we know is that when there's no wavelength shift, I get perfectly constructive interference. So for part A, this is constructive. You may see what's going on for part B. Both of them are 9 meters apart. L1 and L2 are both 9 meters. So when I calculate the path length difference, I get another 0. And we can also say that this is constructive. That's how easy that can be, is just there's no path length difference. Therefore, I know it's perfectly constructive. In the last situation, we have L1 equal 9 and L2 equal 12. And again, I'm going to do an absolute value, so this takes care of the negative sign in here, and I get a path length difference of 3 meters. Well, when I set that equal to m plus a half times lambda, I know lambda is 6. They tell me lambda is 6. So when I divide 3 meters by 6 meters, I get a half. I see that that's a half integer of a wavelength, where m equals 0. So we're at the smallest destructive interference. So I'm going to call this destructive interference. So when you're considering interference, you need to consider the path length difference. When you're solving problems, focus on figuring out path length difference. Another special case and topic in interference of waves is beat frequency. And what happens is two waves of two different frequencies are interfering with one another. And what you can see is that there's alternate reinforcements and cancellations. Here's destructive and constructive. Notice when their peaks line up, that's constructive. When the peaks and valleys line up, that's destructive. And so I have two different frequencies, and this doesn't happen all the time. It happens at very specific cases, right? So the beat frequency, here's like the wavelength for the first one. Here's the wavelength for the second one. You can see that the beat frequency happens at a larger value of both of those. When those both line up with one another, it's not going to happen on the frequency of the first one. It's not going to happen on the frequency of the second one. Examples of these is modularization in radio waves, frequency modularization, so that's FM. And also it's heard with throbbing effect with sound waves. You might hear this if you have different types of instruments. So here's the FM. Just for your own knowledge, it's interesting to know this, how AM and FM works. AM means amplitude modulated down here. So the carrier wave has an amplitude, and it's very consistent. This is the carrier wave. It's one value. The audio, what you want to transmit in that radio wave, has the different amplitudes, whatever is being sounded. And you take those two and you add them, and you get this amplitude modulated wave. This is not beat frequency. Beat frequency is here. That's beat frequency, where I have a carrier wave and I have the audio signal. And when I add those two waves, and you can see here how the frequency of the first wave and the frequency of the second wave, when you add those together, you get a different frequency for this third wave. That's the resultant wave. And this is what we call frequency modulated. How do I figure out the beat frequency? The beat frequency is two waves consist of different frequency. They're interfering, and the beat frequency is the difference between those two waves, and we have the absolute value. So wave 1 will have a frequency and a wavelength. Wave 2 will have a frequency and a wavelength. We look at those frequencies and subtract those, and we will get the beat frequency. I've picked a couple of examples to look at this. The first is a very straightforward beat frequencies of a piano. What beat frequencies result if a piano hammer hits three strings that emit 127.8, 128.1, and 128.3 hertz. So at 3 times, we have these 3 sound waves being emitted, and they're going to create beat frequencies because of their own frequencies interfering with one another. And so I'm going to call this frequency 1, this one frequency 2, and this one frequency 3. There's 3 of them. So if I want to find beat frequencies, I'm going to have to find the beat frequency between 1 and 2, the beat frequency between 1 and 3, and the beat frequency between 2 and 3. So there's 3 different beat frequencies in here. So the beat frequencies will be, well, I will do 127.8 minus 128.1, and notice I'm putting absolute value signs around this. Another one will be 127.8 minus 128.3, and the last one between 2 and 3 will be 128.1 minus 128.3. And you can see this works very easily. This is a very straightforward equation as long as you know the frequencies you can subtract them and find the beat frequencies. This one turns out to be 0.3 hertz. This one is 0.5 hertz. And this one is 0.2 hertz. If you were wondering if this is how binaural beats work, the answer is yes. You can see that if I take two frequencies, bi, and add them together, I get this third frequency. And how binaural beats work is you put one frequency in one ear, the other frequency in the other ear, and in your brain hears them at the same time, and it creates this effect in your brain. The last problem I picked for us is called time between beats. Two pianos each sound the same note simultaneously, but they are both out of tune. On a day when the speed of sound is 343 meters per second, remember this depends on temperature and humidity, all that. Piano A produces a wavelength of 0.769 meters, while piano B produces a wavelength of 0.776 meters. So they're really close to one another, but not quite. So they're going to have two separate frequencies. It says how much time separates successive beats. And I'm going to note that we want a time in here, not the beat frequency. But I can get a period from the frequency. Remember, period is 1 over the frequency. So if I find the beat frequency, I will be able to find the time between successive beats. They don't give me the frequency, but they give me the velocity and the wavelength. So I know that the velocity of a wave is related to its wavelength and frequency, and solving for frequency, I get the velocity of the wave over the wavelength. So if I want to find the beat frequency, I'm going to take the frequency of A and subtract the frequency of B. And I'm going to call this big B, and I'll call this little b, the beat frequency. So piano B and piano A. The frequency of piano A is going to be 343 divided by the wavelength of A, which is 0.769. I'm going to subtract off the same sort of thing going on for piano B with its speed and its wavelength. When I subtract these two, for this number I got like 446 something, and this number is 442 something. And when I subtract those two, I get, it's not a perfect value, 4.0235 hertz. And that would be the beat frequency. But remember, I don't want just the beat frequency. I want the time between the beats. So I'll take 1 over the beat frequency. So 1 over 4.0235. And when I run that through the calculator, we get 0.24854 seconds. So about a quarter of a second when these two pianos, and I didn't expect it to be very large. They're out of tune, so I know they're about at the same frequency to begin with, but they're a little bit different on each end or whatever. So the wavelengths are minorly different, and so I know the time between those beats is not going to be very large. If they were perfectly in tune and had the same wavelength, that value would be 0. They'd be lining up on each other and amplifying each other. But we get this little bit of shift with these two waves, and their beat frequency is about a quarter of a second.